And so now we're all up to speed on what the disinfectants are and why and where they are important. Let's have a look at some of the challenges of trying to keep them under control and at the right levels. The management of disinfectant levels is especially important in the food and beverage sector. We've already looked at the risks of not effectively managing the disinfection in this industry. Safety is essential. Now, there are a few areas where many customers in the food and beverage industry have expressed pain points when it comes to disinfection control. There are significant cost benefits to managing your water and chemical usage well, while still maintaining the highest standards and keeping your reputation glowing. Water is a pesky thing to analyse. It is naturally non-homogeneous, meaning that it's not the same all the way through. You'll notice that you get warm and cold spots in a pool. Aside from the potential that someone has disgraced themselves, this is usually due to some sort of dead spot when it comes to water filtration. Well, for the water in a dipping tank, it's the same. There will be variations in temperature and in concentration of any disinfectant, any microbes, any contamination across the body of the water. Constant mixing helps with this, but doesn't make the water homogeneous. So because of this, it's important to have a method that gives you data you're confident in and provides you with enough traceability that you can please any auditor. And with all of this in mind, I'll hand you over to Ian for the next section.
Thank you, Hannah. So now that we understand why it's important to be able to accurately measure disinfectants, let's look at some of the ways that we can do this. First option is to build and equip an on-site laboratory. With the right equipment and educated, trained and experienced staff, we can use laboratory analysis techniques such as high-performance liquid chromatography / ion chromatography, HPLC-IC, or accurate digital or manual titrations to analyze disinfectant levels. The results that we obtain with these methods are accurate and reference to standard methods and can be described as gold standard. However, there is a downside. Analyses performed in this way are often slow, and the cost of equipment and suitable staff is high. With this type of testing, there is no option to test at the sampling site, which for highly reactive and volatile disinfectants will inevitably lead to negative bias on testing results. Alternatively, we can install fixed online sensors at critical control points. These systems give constant feedback on the parameter being tested and allow on-the-spot trending and empower decision-making. The response of fixed systems change over time, and regular calibration and validation is required. Furthermore, it's not cost-effective to install online analyzers at every control point, and importantly, online systems for each parameter required are not always available, and these systems are still subject to human errors such as calibration errors. To move the testing close to the sampling site, we have a number of field testing options. These include test strips, similar to a pH test that you would have done at school, where a strip is dipped and color change compares to a chart to give a result. Alternatively, a drop count, a titration mimic, where a number of drops of reagent are added until a color change is reached, and the number of drops used is multiplied by a factor to give a result. These types of testing are accepted as being of limited accuracy and precision, and the way that they work involves a significant amount of subjectivity on the part of the user, which affects consistency of result from person to person. Instrumental tests, such as colorimetry, remove the subjectivity and can provide a much better precision and accuracy. However, since they rely on light transmission for the test function, they do not tolerate highly colored or turbid solutions. They also don't have an inbuilt temperature correction function, and results can be affected to a large degree by user technique. Some of the problems of reagent-based testing techniques can be overcome by using electrochemical techniques, so let's talk a little bit about them. The technique that we have turned to is an electrochemical method. Electrochemical methods such as pH and conductivity measurement can be very precise and very robust, allowing excellent accuracy and precision under challenging test conditions. Chronoamperometry uses a classic 3-electrode system to measure changes in current over time. In this case, the current change represents the reaction of the oxidizing disinfectant on the surface of the electrode. On the graph, C1, C2, and C3 represent 3 different concentrations of oxidant reacting over a period of 60 seconds. Integrating under the curve gives the concentration of the oxidant. Palintest's sensor technology products use a potentiostat to control and measure the electrochemistry of redox systems very precisely to give high-quality analytical results. This animation illustrates in more detail how the chronoamperometric analysis proceeds. The Kemio instrument will deliver two different voltages to the sensor across the test time of 1 minute. And the current that the sensor returns to the Cameo is measured over that minute. The size of the current is affected by how much of your target analyte is present, and with a bit of maths, this current change can be converted into a concentration for your target parameter. The key part of the technology is the sensor. Sensors are made of 4 electrodes printed onto plastic substrates using conductive inks. The sensors are then dosed with chemical reagents. Selectivity comes from the chemical indicators dosed onto the surface of the working electrodes. For example, one set of reagents will be used to make a chlorine sensor, another set a PAA sensor. Having 2 working electrodes on one sensor gives great flexibility and allows, for example, one working electrode to measure free chlorine and the other to measure total chlorine on the same sensor, or for each working electrode to be tuned for high and low ranges of the same oxidant, giving excellent response across a wide concentration range. The sensors are single-use and disposable and give a functionally reagent-free system. So that's the sensor. This is the instrument. This is Kemio Disinfection, the measurement platform that uses the sensor to give results. The touchscreen interface makes ease of use, allows more information and instructions to be shown on screen, and more user information to be input. Upgraded electronics from the previous instrument generation give a wider measuring range, enhanced repeatability, and powerful data management and download. With the instrument, batch calibrations for each batch of sensors are uploaded to the instrument. This is now done by scanning a QR code printed on the sensor box. Individual sensors are also scanned before use to ensure that the correct batch calibration is available. This is also an important quality assurance step as it makes sure that the wrong sensor cannot be used for a test. The large color touchscreen on the instrument displays graphical instructions, which takes users through the testing protocol step by step. You can see full details of operation and visual instructions on our YouTube channel. The Kemio data handling setup gives full traceability of results. Sensor scanning records the sensor batch used for each test and confirms that the sensor is within the expiry date. User IDs and site labels can be set up for further record keeping. Process control pass-fail limits can also be set up to immediately inform an operator if the system is under control or whether they need to take corrective action. 10,000 data sets are recorded automatically and cannot be deleted from the instrument, giving a full audit trail and losing the ability for users to falsify results. The test method overcomes dependence on technique and conditions. Colored and turbid samples can be measured with no effect on the result. The measurement technique gives access to wider measuring ranges and with better low-end sensitivity. These features give access to a wider application set. The built-in thermometer gives automatic temperature correction. Sample volume does not have to be precisely measured, and the absence of reagents give a reduction in sample manipulation. This means that common sources of error are eliminated. The absence of chemical reagents in glassware mean that the system is suitable for applications where glass and chemicals are restricted. This is very important in the food and beverage sector. There's such a wide range of testing methods for analysing water in the field that choosing the right one for you can be tough, as not all methods are made equal. The general decision is between how easy it is to use and how reliable and accurate the results you get are, and which is most suitable for the application you're working in. Here on the slide we have a matrix which has an axis that runs from easy to do up to hard to do, and then left to right we have the potential accuracy. And this is a measure of the quality of results that you can achieve. Easy to do visual tests like test strips and drop count kits are generally quick and can be done by unskilled users, but the quality of results is relatively low. These methods sit down here. With lab methods, such as titrations, you get much more accurate results, but these require a highly skilled operator and generally take much longer to do, so these sit at the top up here. A sweet spot in between these is the photometer and reagents setup. These offer higher accuracy and precision than the visual techniques, with a method that a trained user will easily be able to carry out. The sensor method, however, is able to provide much more accurate results, but with an easier method. The sensors are like a test strip in that all the reagents are pre-dosed, so you just have to put it in the instrument with the water sample. So this sits down the bottom right, which means best results, but very easy to do. There are Kemio sensors available for testing key F&B disinfectant parameters. Chlorine is very widely used across the industry. It's effective, low cost, and easy to handle. With Kemio, you can test up to 500 milligrams per litre of chlorine and discriminate between free and total chlorine across much of the range, although there is a clear trend towards measuring and reporting free chlorine only. Chlorine dioxide must be generated in situ for optimum results, but is a more potent disinfectant than chlorine and is effective across a wider pH range too. Peracetic acid is another disinfectant of interest, and again is more potent than chlorine and does not form some of the harmful disinfection byproducts that chlorine can. Cameo can measure these disinfectants down to very low levels, and the measurement ranges are designed to cover most applications without the need for sample dilution. In the last 18 months, we have trialled and launched a number of new sensors. Our new instrument and our new sensor manufacturing line means that the rate of release of new parameters and ranges will continue to increase. So let us now look at some applications in food and beverage where Cameo is being used to improve processes and results. Our first case study is poultry processing. Use of oxidizing disinfectants in poultry processing is a topic that has been controversial internationally and is not practiced in all countries. I don't intend to get into the rights and wrongs of it here, but it does make for a very interesting case study. There are two main areas that you'll find disinfectants in this process. The first is to clean carcasses immediately post-slaughter using a spray or dip bath. Secondly, an oxidizing residual is maintained in the chilling bath that is used to quickly bring the temperature of the chicken down to improve shelf life of the final product. This application can be found to use a range of different disinfectants, and chlorine dioxide and PAA are growing in popularity due to the advantages discussed previously. The proponents of using disinfectants for poultry washing will tell you that one of the main advantages of this process is to allow reduction on the reliance on antibiotics during the animals' lives. Some important points in testing washing and chilling waters in poultry processing. The samples that are taken can be highly coloured with blood and other bodily matter and can be turbid from undissolved materials and fats. This makes colour-based testing unsuitable, and colorimetric testing can fail due to the turbidity. Furthermore, online testing probes can be fouled by this organic material. Traditionally, drop count testing has been prevalent in this industry as the best available option. However, it's recognised as not satisfactory in terms of analytical results. And, as with all food safety applications, there is a significant requirement for audit data to be available for internal certification and to satisfy customer requirements in food service and retail. Our next application is much less controversial, as known as aseptic filling. This is used in the production of bottled juices, iced teas, and related products. PET bottles are blown on site or brought in and washed with disinfectant to provide a sterile environment. The sterility of the product means that refrigeration of products is not as important for increased shelf life, simplifying and reducing cost for onward supply chains. This is a classic PAA application, not least because chlorine has the reputation of making polymers brittle. Also, the volatility of PAA is a virtue, as the final step before filling the bottles is a sterile rinse to get the PAA level down below 0.5 ppm. This is an FDA limit. When testing PAA in this application, there's some interesting points to consider. First of all, there isn't a huge amount of choice for field tests for accurately measuring PAA. The Kemio system does represent by far and away the preferable option. Secondly, this is a multi-step process with a range of testing points. There is bottle sterilizing, usually a separate cap sterilization process, and let's not forget the sterile rinse step to remove the PAA. There is a requirement for testing at all of these critical points, and depending on the process, you will find a range of concentrations from less than 0.5 ppm to in the rinse water to greater than 2000 ppm in the sterilization steps. Aseptic filling also uses heat to assist the process, and sample temperatures from ambient to greater than 50 degrees C are present, which means that any technique used must be able to measure and correct for these wide variances in temperature. Final application that we'll consider is fresh produce washing. This is typically the washing of vegetables and fruit for processing into ready-to-eat products, such as bagged salads for supermarkets or lettuce for food service use in restaurants. The produce is typically washed clean of soil, organic matter, and other contaminants in a bath, flume, or using overhead spray jets. A key feature of this application is that for water efficiency, the washing water is often recycled and reused in the system, sometimes for a whole growing season. In this situation, one of the main purposes of the disinfectant is to prevent microbiological cross-contamination from one batch of produce to the next. This also requires a number of critical control points to be set up after disinfectant dosing and at each discrete process point. Chlorine is the typical disinfectant used for this application and is used in a range of different concentrations up to 500 ppm depending upon the vegetable or fruit in process. In this application, the water will often be dirty and turbid from the soil, leaves and other particulate matter washed from the produce. Temperature variation can play a part due to the open nature of the processing plants, which tend to have a range of ambient temperatures depending on the location and season. Given that the customers of these products are usually supermarkets or chains of restaurants, there is a very stringent food safety audit regimen in place. This is important for two reasons. First, that traceability of results is key. The ability to prove that carrot A was subject to the correct level of disinfectant, for example. Secondly, there are process audits as well, which means that the plant will have to prove that their testing is correct and repeatable as a process, which is more difficult for testing methods that are complicated or subject to large numbers of potential errors. Finally, agricultural sectors are seasonal and have a fluid workforce, so that having a testing method that gives excellent results but without the burden of large amounts of training for new starters is very important. So today we've shown you why Cameo is useful in food and beverage disinfection testing. It covers the relevant disinfectants in the right measurement ranges with the required sensitivity at low concentrations. The technique is accurate, robust and repeatable across all users and sample types. The instrument provides detailed, secure and auditable data, and stakeholders in the F&B sector that are using Cameo are fulfilling their HACCP and food safety requirements more fully and simply, and can evidence direct cost savings from the proper control of dosing chemicals.